primary interest lie in statistical machine learning, Bayesian statistics, probabilistic graphical models, and large-scale optimization. And particularly, he's one of the leading researchers in deep neural nets. So it's a nice transition from the previous talk. He is a recipient of the Early Researcher Award, the Kano New Researcher Award, the Arthur P. Sloan Research Fellowship, the Microsoft Research Faculty Fellowship, and he's also a fellow of the Canadian Institute for Advanced Research.
Thank you. So let me just start by saying that in the theme of this workshop, we've been seeing a huge increase in the amount of the data that we see today, as well as the amount of computational resources, right? So if you look at the web, we have images, video, we have text, we have speech. If you look at product recommendation systems like coming from Amazon or Netflix, look at relational data, social networks, lots of scientific data available to us, right? And one of the things that we're interested in is how to develop models, statistical models, models that can discover interesting structure from the data. In particular, how can that be done in unsupervised or semi-supervised way, right? So this is the case where you look at all of this data. A lot of the data that's available to us come in the form of unlabeled data. I can get lots of images from the web, but it's sometimes pretty hard to get labels for those images, right? So how can we handle that situation? And one particular framework that I'm going to talk about is learning these deep hierarchical models, models that support inferences as well as discover structure at multiple levels of representation. So I'm going to talk about three things. I'll briefly introduce deep learning, but then I'm going to focus on some of the recent advances. and these include learning more structured models, in particular looking at transfer learning problems, as well as looking at multimodal learning, so where you're trying to learn from multiple data sources. Okay? So let me just briefly start with one particular slide. A lot of work in deep learning is focusing on graphical models. Right? And graphical models, they offer a fairly powerful framework for representing structure, dependency structure between random variables. And one particular building block for deep learning models is this model called restricted Boltzmann machine. It's a Markov random field. You have stochastic binary visible variables V, and you have stochastic binary hidden variables. So you can think of visible variables as, let's say, pixels and images. Right? And you can think about hidden variables as feature detectors, trying to find some interesting patterns that you see in the data. And you have very specific connectivity structure to that particular model. Now, you can specify a proper probability distribution here. So you can specify what's the joint probability distribution within observed nodes and the hidden nodes. And you have a fairly standard type of a model, undirected graphical model. Sometimes it's called Markov random fields, Boltzmann machines, log linear models, right? The most particular term is the pairwise term here that essentially models dependencies between observed variables and hidden variables. So that allows you to find certain structure that you see in the data. And the reason why these models are called generative models is that we can look at conditional distribution. So we can look at conditional distribution of observed data given features, and that takes a simple form. It's just a product of marginals, where each marginal is given by a logistic function, right? Now, I'm not going to tell you about how we do learning in these models. There are techniques for fitting parameters in this model, but I'd like to show you what kind of features that this model is extracting. So if you look at one particular data set, this is a data set that was collected at MIT. You have about 25,000 different characters coming from different alphabets around the world. If you fit one of those models to that data, this is the kind of structure that the model is discovering, right? So it has these kind of edges, stroke-based structure. And the way to think about this model is that if I show you a new image, right, I can do inference in that image, and I can basically figure out that this image is made up of these three strokes that you combine together. And typically, the numbers here correspond to the probability of that particular feature appearing in the image. And you get fairly sparse representation. So in the back of your mind, you should think about these kinds of models as finding low-level structure in terms of finding interesting bases. Right? The nice thing about these models is that you can extend them to dealing with other data modalities, right? So if you look at real-valued data such as images, then this is the structure that it's finding. So it finds little edges. And again, you can think of it as each image is made up by some linear combination of the edges that you're seeing here. Right? And a lot of them look, there's some color components and some edges. If you look at text type of data, right, and you ask the model to find the structure in that data, this is the kind of features that the model is extracting, right? So you can see it's basically finding topics in the data. So you have topics about Soviets, you have topics about US presidents and computers and stocks and so forth. And you can think of that particular model. What it's finding is that you're saying each document is made up by some linear combination of these topics. So it's exactly the same model, just different data modalities. One other particular application is collaborative filtering. This is where you have users and you have items. You're trying to find ratings between users and items. And the model can be extended to working with social networking data. But the interesting thing is here we've looked at the data where you have about 500,000 users, about 80,000 movies, about 100 million ratings. And the kind of structure that the model is discovering is, if you look at these genres, it sort of picks up on particular genres that you see in the data. So it's essentially finding what kind of movies the users might like, and it's interesting to see that Michael Moore gets his own hidden unit, hidden variable dedicated to him, just because most of the people either like his movies or they hate his movies. So that kind of patterns the model is extracting. Now, the idea behind deep learning approaches in general is that if you look at sort of these simple models tend to capture first-order structure, right? So you're finding local edges in images. And if you start building more complex models, right, the hope is that you can learn hierarchies of nonlinear features. And the idea is that you'll have high-level features that will capture, in this case, it's capturing combination of edges. So it captures some high-order structure. And the way you should really think about these kinds of representations, that these nodes, the low-level nodes, they're capturing to some extent first-order correlations between the observed variables, and these nodes are capturing correlations between the second-layer nodes. So you're trying to find some high-level dependency structure that you see in the data. And the beauty of these models is that they can be trained in completely unsupervised fashion, right? And one nice thing about these models is, again, there's a very natural notion of bottom-up and top-down. So whenever you do inference in these models, information propagates up and down in this model, right? That's sort of one of the advantages. In particular, if we look at the Reuters dataset that John was talking about, and you look at the high-level structure that it's discovering in completely unsupervised settings. So I'm not telling the algorithm particular labels that you see in the data, and this is the two-dimensional embedding of the data. Right, so it finds different topics, and and one interesting thing that it finds, if you look at European Economic Community stuff, it sort of puts it next to disasters and accidents, right? So that's the data was collected in '96. So I guess today those two lines would be closest. If you're looking at using these models for information retrieval, right? There's a lot of dependencies between these two topics. That you can really think of this model as a nonlinear version of PCA, right? And you have about 800,000 stories for that. If you're looking at the speech recognition, I think these models have had a big impact in the speech recognition communities. If you take the model, in particular, this was done for the spoken query detection task. If you look at performance of these models compared to standard techniques like Gaussian mixture models, you have big gains, and I think that. My feeling is that I don't work in the speech community, but my feeling that in speech communities, these models are really revolutionizing speech recognition systems. Particularly as far as I know for sure that if any of you are using Android phone, then these kinds of models are doing speech recognition. So next time you talk to your Android phone and it doesn't understand what you're saying, you can blame deep learning for that. But let me just talk a little bit more about recent stuff, and the idea of transfer learning, I think, is an important class that we're trying to pursue, in particular when we look at large-scale data. Imagine that we have the following problem. You have millions of unlabeled images, and you have some labeled images, right? And the hope is that how can you take this background knowledge and learn quickly about a new concept, right? So in this case, you're trying to learn from a single image of a Segway. Right, and then you start testing of what other images of Segway might look like, right? And so And it's a key problem in the vision, speech, and natural language processing in a lot of different other domains, right? And one of the things that we've been looking at is how can we transfer knowledge from this big background set to learning new concepts from few examples, right? And the idea is that if we look at the Segway, you can say, well, it's a kind of funny looking vehicle, and you might know something about other kinds of vehicles, right? Motorcycles and unicycles. There is also a notion of high-level parts, right, such as wheel, hand, and post. And there's also a notion of low-level parts, low-level features like edges. So we've been looking at the models where we're trying to build hierarchical models where at the low levels, we're learning low-level generic features, such as edges, combination of edges. And at the high level, we're looking at the hierarchical structure, how different objects are related to each other. And the hope is that if you look at the vehicle class, you might say a lot of objects that belong to this class will share the same high-level features, right? Objects that belong to the animal class will share some other high-level features. And you're trying to figure out what these high-level features are and what's the relationship between different objects. And this is the kind of hierarchy that you get to learn. You get to learn low-level features. Those low-level features get combined into high-level features. And then there's a whole hierarchy of how different objects are related to each other. Right, and the hierarchical structure is being learned with something that's called hierarchical Bayesian type of models, and the low-level structure is learned with a deep Boltzmann machine, right? And we can ask the model to see how it can learn from a few examples. So if I show you 3 examples of apples, and I ask the model to generate other notions of what it believes apples should look like, it draws these things. And I should point out that in these models, we don't put any prior knowledge about images, so there is no notion of how images should look like. Everything is being learned from the data, from 4 million images. If I look at the willow tree, this is what it generates. It kind of looks like Picasso drawings. If you look at the rocket, this is what it generates. This is sort of a generalization of what it believes those images should look like. And if we look at the handwritten character recognition, if we look at these handwritten characters, we can see at the low level you're discovering edges, but at the high level you start discovering notion of strokes, right? And it just naturally comes up from that particular data. We didn't make any adjustments to telling the model that you're working with one particular data modality or another. It just naturally comes up from these models, which we believe is the right structure when we're parsing handwritten characters. So that's, and it gives us pretty big gains in terms of recognition accuracy when we're trying to recognize what handwritten character we're looking at. Right. And let me finally just briefly talk about multimodal learning. How can we extend these models to dealing with data where we have multiple sources of modalities, right? If we look at a lot of multimedia contents on the web, we can see that images are typically associated with text. If we look at product recommendation systems, or if we look at robotic applications, and there's a lot of multimodal data that we see today. By the way, I should point out it took me a very long time to prepare this slide, so I hope you enjoyed it, all the animations. The idea is that if we have images and text, then we'd like to get some kind of a concept from both of these different modalities, right? And what we've been looking at hierarchical models that build high-level representation. So you have an image pathway, right? You're trying to take image and extract some high-level representation. You're trying to take text, a bag of words representation, and extract high-level representation, and then you're looking at modeling dependencies between 2 of these modalities. There is also a very natural notion of bottom-up and top-down, so the information floats from one modality to another modality, and lets us handle both of the data pretty reliably, particularly when we're working with noisy data or missing data. There is also mathematical formulation behind this. I'm not going to parse what these equations are like, but I'd like to point out that it's a probabilistic model. We can define the probability distributions over these different modalities. We can do proper inference and such. So here's some examples of what the model is capable of doing. So I show you an image like this. And this is what it generates, or at least these are the samples that you get from the model. So it does find some interesting structure. Most of these things look reasonable. So it does capture what's going on in the images, right? And of course it's always fun to show some failure patterns here. These are the failed examples. So if you look at this image, right, I just think it's an army soldiers of women, right? Or if you look at this one, right, you can guess why that's happening. And the reason why this is happening is that, you know, Obama signs have a lot of bluish and white signs, right? One of the things is this was done on the Flickr data set, and what's happening there is that there aren't that many images of animals. So there aren't that many images of tigers, right, or lions. Most of the time people just post the photographs and their portraits and such. So we believe that's the reason why the model is making those mistakes. Right, but we can also go the other way, because we're building a multimodal model. We can do a query the other way around. So given some words, these are the retrieved images. Right, so it does fairly well on a number of tasks, but then this is a particular failure case, right? If I ask for chocolate cake, it sort of retrieves these guys. And that kind of looks like chocolate cake. I think these are two bugs, right? So let me just point out that, you know, this line of research we've been focusing on, and we've been focusing on and also looking at speech and audio, trying to improve speech recognition by looking at the video, flip movement, as well as the audio. And it's really is the case that I think that developing systems will have to take multimodal data into account if we want to develop systems that come closer to displaying human-like intelligence, right? One of the key challenges that we're facing is inference in this model, inference and learning. How can we take these multiple sources of data and really fuse them together? So let me just summarize. You know, if we look at deep learning type of algorithms, and there's a lot of applications in vision, in natural language processing. If we look at trying to build a category structure of relationship between different objects, speech recognition, trying to deal with multimodal data, and more recently we've started looking at object detection, using these deep learning models to do object detection. We have some success stories there, and it's really is exciting because these kinds of models improve on the current state of the art in a lot of different application domains, right? Ranging from object recognition, object detection, text image retrieval, and speech recognition. The beauty of these models is that they can be employed in different variety of different application domains, and they can handle large volumes of data. So a lot of the models that I'm showing to you are built on data where we have millions of examples. And just to finally summarize, if you look at the impact of deep learning, we've seen a huge impact in speech recognition, in the vision communities, and recommender systems. And more interestingly, right now, drug discovery and medical image analysis is also embracing those kinds of models. In particular, Merck and Novartis have been looking at using deep learning for drug discovery. Okay, and I think I'm not going to hold you longer because I think that everybody's trying to get some coffee. So thank you. Well, I think that if I go back just briefly to these ones, yes, we haven't done, so right now these are just qualitative results. We don't know how good they are, right? In terms of evaluating these models, one proper way of evaluating these models was for us to do image recognition. So we were trying to see whether these additional captions could help us recognize what class this image belongs to, like a cat class. But we haven't really done sort of a quantitative estimation of how good that representation is. These words are, yeah. I mean, I can show you some of. This is an example where you're running the model, you condition on that particular image, and these are samples drawn from the model, right? So you can see that, you know, it tends to say that it's a ocean, beach, wave, sea, sand, beach, island, travel, and then occasionally it goes to water, Canada, BC, Italy, water, sea, boats, Italia, and then it goes to, you know, sometimes it goes to other parts of the space, and then California, beach, landscape, ocean. So it tends to sort of find different kinds of different alternative explanations as to what this image might look like, right? It thinks now it's in California, somewhere in Pacific, and now thinks it's in Mexico, Brazil, and right. right? Just people traveling and such. So, but again, yeah, we don't have any quantitative estimation of how good of a generative model that is. Yes.
Any